Okay guys, I would like to welcome you to the second part of my pH series in hydroponics, and we're gonna talk about uptake and pH today, which is basically molar concentration in application. Give me 20 to 30 minutes and you know what I mean. Okay, so in the last video I said I want to briefly explain you what a pH is. And you see this chart here, and on the left side we have concentration in millimolar, and here at the bottom we have the pH value from 0 to 14. And you see these two dotted lines here. The blue one is H plus and the green one is OA minus. And you see that you have at any pH, you have a molar concentration of either both. And at 7, they have the same concentration. Okay, so when you think of the pH, you could think of a number or you could think of a concentration of either H plus or OH minus. So if you know, for example, we have a pH of 5, then you know that, wait, we have a pen here. Let's talk about a pH of 5. So we have a molar concentration of H plus at 0.01, and we have 0.12345, 501 of OH minus. Okay, and so your pH number that everybody uses is basically saying that you have a concentration, and of course you can calculate that. So what you need to type in your calculator is minus log and then in brackets, and we require the concentration in mole, not millimole. I used millimole in this chart, otherwise the numbers would be a lot longer, or I would need to show them in a different way, but I like whole numbers in this case when I show you that. So if you type in that, for example, as a concentration of H plus in mole, not millimole, then you get 3. So this is 1 millimole, I think. Is it 1 millimole? Yes, it's 1 millimole, 0.001 mole. So if we have that concentration of H plus, we have a pH of 3, and pH is in mole. Okay guys, so we've just learned that H plus is basically our pH, our proton concentration. So I would like to talk about the basic principles of base and acid. But we start with acid. So remember chlorine from the last video. So when we have HCl, so we have hydrogen and chlorine. When this is in water, hydrogen gives the chlorine its electron because it's attracting the electron. And what stays here at the hydrogen is just a proton, because hydrogen has a proton and one electron. So HCl, it has no charge, but in water it falls apart in H plus and Cl minus. And this is an acid. So our concentration of 0.001 mole, so 1 millimolar HCl, had that pH of 3. So we have 1 millimole H plus and 1 millimole Cl minus. Okay, and that counts also for example, for nitric acid. You can replace what you have seen in the first video, nitrate, you could replace that here in that example. Okay, now we need to talk about a base. In this case, potassium. So what we have here is potassium hydroxide. And in water, the potassium gives the OH minus its electron. So what stays over is K plus and OH minus. And let's say again we have a concentration of 1 millimolar, 1 millimolar potassium hydroxide in water, in solution. What's the pH of this? So we need to go back to that chart and we could read it out. However, we use the same principle of calculating the pH, but we have a base and we need to calculate the so-called pOH because there is always a pH and a pOH. And of course, it's also in mole. And it's again 3. But your pH is not 3. Your pOH is 3. And your pH, now we need to bring pH and pOH together. It's very easy because pH plus pOH is always 14. Always. And we know our pOH is 3. So what's our pH? It's 11. So this is how you calculate your pH when you only have information about a base that is in your solution and you only have the information about OH minus concentration. So let's make a summary of that brief pH lesson. So every solution has a certain H plus and OH minus concentration. That was the chart I've shown you, no matter what is inside that, even if it's pure water. And the reason that pure water also has a pH is because when you bring that together, then you have H2O. And water, it always falls apart in this and goes back together. It's doing that all the time. So this is the reason why if you don't have any chloride or nitric acid, potassium, whatever inside the water, this is why you find H plus and OH minus. Okay, and we measure the pH in a molar concentration of H plus. Okay, so when you think of pH, as I said in the beginning, you can think of a number. And now you can think of a concentration of H plus, and OH minus. And that concentration, it depends what you brought into the water. If you bring, for example, imagine in this image you only had an equal amount of potassium and nitrate. So there would be no H plus because when you bring that as a salt into your solution, your pH is in balance because acid and base together they form salts. Okay, so keep that in mind. Try to imagine more what is going on in your solution, what particles are in that, than rather thinking of a number, okay? Okay, now we come to the interesting part. So you might thought that in PowerPoint, this is supposed to be a lightning, but you were wrong about that. That is a root, okay? And this outside of the root or the root tip, it has a membrane. And a membrane is something biological that where you can separate different areas in cells. And membranes also can be connected to the outside, like in case of a root. That's not all plant surfaces have membranes at the outside, but the root tips have, because this is where the nutrient uptake takes place. Okay, so this one here, this one here is the membrane. So basically, this is all membrane you can imagine, and just imagine that in the membrane, there are transporters for cations, anions, so positively charged atoms and negatively charged atoms, or you can say for base and acid. Okay? Okay, now we have here our membrane. This is outside the root, this is inside the root. And imagine we had, where's the pen? We had 1 millimolar of KNO3 outside the root, okay? And that, of course, is a salt, and in solution, it makes this K plus and NO3 minus, as you can say here, okay? And think that transporter, it is able to transport potassium, and it goes through the transporter inside the root, okay? So what is happening then? What is happening then is you get a H plus in exchange, okay? And now you see in our example we had 1 millimole of KNO3, but the K is gone. It's inside here now, we get an H plus. So what we have now is we have 1 millimole of nitric acid basically. You can say this is nitric acid. In solution we have, of course, H plus and nitrate, and you see this results in a pH drop, because when we had potassium nitrate outside, KNO3, 1 millimole, we had a base and an acid. So the pH would be neutral. But we lose the potassium because it's transported into the plant and we get an H plus in return. So what has happened here is we see a pH drop because we lost our base and we got an H plus in return, and what we still have is nitric acid. Of course, this also can go the other way. We get a rise in pH if we lose our nitrate. Remember, we had KNO3 at neutral pH, okay? We lose the nitrate, and we get OH minus in return. So we have K plus and OH minus. And in both examples we have, I said we have 1 millimolar, okay? That could also be 2 or 0.7 or whatever concentration it doesn't matter. It's just to illustrate what is going on at the root tip when plants uptake the minerals. So we have left 1 millimolar OH minus, okay? And this is why we have a rise in pH. This is a little bit oversimplified because I think state of current view on this is that you don't get H plus back, but you know the plant is permanently pumping H plus over the membrane. What, by the way, requires really a lot of energy because that has to do with the concentration between outside and inside, and you have to transport what is outside. Here is a lot higher concentration of atoms or ions inside the root, and you want to transport against the concentration gradient. And this is why you require energy for this, otherwise that would work alone because it's always trying to balance, you know. But that's a complete different topic. What I was trying to say is when you get H plus and you get another one, okay, and then you take the nitrate, with 2H plus, okay. And if you remove 2H plus and nitrate, so this is in balance, but here you have left over an OH minus. And that OH minus, it can only be balanced by a proton or by a base like K plus, okay? But if you remember, when you can remember, you remove an acid, you have a pH rise. You remove a base, you have a drop. Okay. Okay, guys, and here it comes. Now we are going to link millimolar and pH. This is our solution from Hoagland that we have seen in the last video. You see, it's not so easy to write with this. I think you can read it, okay? So I'd like to summarize what we have in total nitrogen. We have 15 millimole. We have 14 nitrate, 1 ammonium, phosphorus, 1 potassium, 1 calcium, 6, 4, and so on and so on. Let's imagine we have an uptake, okay? And now you need to focus how many charges every particle has and whether it is negative or positive. For example, you see here we have ammonium and phosphate, and you see we have 0, 0. So let's just cross that out, okay? Because just imagine both was taken up. First, for this you got over your membrane. So I draw a membrane here. So for the ammonium, if this is gone, you receive H plus, 1 millimole, okay? And H2, PO4, you basically receive is 1 minus. You basically receive OH minus, and then we have a water molecule. Okay, so if this is gone, if both are gone, we have left water, a water molecule. Well, in case of magnesium sulfate, we go from 2 to 1 in both cases. Okay, I make this example that it is relatively easy to imagine. So what do we have left? We have nitrate 5, okay? And we have calcium, which has 2 plus, that's very important, 2 plus. So you learned that in the first video. We have 2 millimole of calcium, which has 2 charges. So this can balance, so it is 4 charges. So we require 4 positive charges, so we require 4 negative. So we take from the nitrate, we take 4, and 1 is left over, okay? We take these 4, and the calcium is balanced. And what's left over? 1 nitrate, that's gone now, and 1 potassium, that's also gone. So in that example, I was trying to show you what happens to your pH when everything is taken up more or less. And this is an example where I wrote it here, uptake is complete imbalance. But normally this is not the case. That imagine you meet the demand of the plant, like you know that, okay, you require 15 millimole of nitrogen and 6 of potassium. You can assume that, so let's say to 70 to 90%. And of course it's a dynamic, and these processes when it is exchanged at the membrane, yes. So the pH, if you had a curve of if this is a timeline and this is your pH, and imagine all that uptake, like we start at 5 point, okay, we have 5 point here, and of course it goes like this, yeah, but this is fine, you know. The target, what I'm trying to show you with this is, let's say your composition of your, we will talk about that later, this is the most important topic. Imagine your composition is not so good and something is left over, like you have calcium like 7, okay, and the nitrate is taken up because nitrogen is always taken up, and then your pH goes like this. Now what do you do then in hydroponics? Acid plus acid, okay, because you want your pH to be in a certain range. This is how most people work, but we will talk about these dynamics of the pH, we will talk about that later. Okay guys, now I would like to show you an example that is some more realistic when we link millimolar and pH. So let's cross out what is in balance, that we can imagine that a little bit better. I made it like that ammonium and phosphate is in balance. Magnesium and sulfate is in balance. So what do we have left? We have, this is supposed to be 0 then. So we have 7 of nitrate, and we have 3.3 of potassium, and we have 2 of calcium. And here you see that we have a higher concentration of OH minus. So we have 0.3 millimole of OH minus. So we want to know now what the pH is. So we calculate the pOH, and that's wrong, by the way. There is 1 0 missing. You see, I'm only human. So let's see what does ChatGPT calculate. Okay, so what does ChatGPT bring us? We have a pOH value of 3.52, and when we calculate the pH, we have 14 minus 3.52, we have 10.47. So yes, that is relatively high, but you need to consider, in my example, I left a lot of nitrate. And by the way, the pH can vary in the root zone a lot. So it can, for moments, it can go relatively high, but then drop significantly after a lot of base is taken up, or the other way around. Okay, so in this example, our uptake is not in balance, and we have a lot of nitrate left over. So this is why we result in a pH that is relatively high with 10.47. Okay guys, what is the takeaway message? What was important? We have seen nutrient uptake by the example of potassium and nitrate. And we have seen that we basically exchanging H plus and OH minus, how it affects the root zone pH, which at the end of the day, of course, it affects your entire pH of your media, of your cocoa, of your rock wool block that you have in recirculation, and that at the end of the day, this is gonna affect your pH of the solution that you use when you have rock wool in recirculation, for example. And we have seen, how do you link the constitution of your solution and the pH in molar concentration. So this is the important point. We talk in this regard about molar concentration when we talk about uptake, because we can directly link what has been taken up to the pH, because we know in molar units what we get in return. This would not be possible if I told you that 1 millimole of nitrogen is 14 milligrams and 1 millimole of potassium is 39 milligrams. And I told you, give you two numbers, what has been taken up, and you say, oh, I don't know. what I got in return, so I cannot calculate the pH. So you see, when you think what is in your solution, you can do that in ppm or milligram per liter. You can do that, no problem. However, when you think in molar units, then you can link that directly to the pH. And that starts when you imagine when you make with that calculator I've showed you, when you make the constitution of the solution by adding whatever you want to add, and then you try to imagine what is going to be taken up, and this will be the fate of your pH. Okay guys, so in the next video, what can you expect? We take a deeper dive into controlling a solution and a pH. And meanwhile, I think you know what I mean when I say controlling a solution and its resulting pH. It has always to do with the original idea and the uptake, and what results from that is your pH. So you can say we take a deeper dive into the fate of your solution and its resulting pH after uptake. So we will see more examples, and I would like to show you how to work or what is supposed to be in your solution that you do not have to add like enormous amounts of acid, for example. So with that said, thank you for watching. Please like the video, please subscribe and leave a comment if you want. Bye bye.